Hello and welcome back to another episode where I'm about to share with you the solutions for the weekly coding challenge number 35. So, before you quickly get into it, don't forget to go and check out the solutions for weekly coding challenge number 33 and 34. You can find the links in the description below. Let's get into it.
Hello everyone, so today we are going to solve another question on Unstop practice, that is smart parcel delivery. Now the problem states that in a futuristic city, autonomous drones deliver parcel across the 2D grid of buildings. Each cell in the city represents a building with a landing cost, the cost in energy units to land on that building. A drone starts at the top left corner 00 and must reach the bottom right corner n-1 and m-1. It can move up, down, left or right but cannot fly over buildings with a landing cost of -1. These are restricted zones. Your task is to compute the minimum energy the drones need to spend to reach the destination. The drone must pay the landing cost of each building it enters. If it's not possible to reach the destination, then return -1. So let's try out this example and then we will understand the problem. So here we have number of rows and number of columns as 3 and these are the values in that. So if we try to see this again, we will start from here, this value. We will start from here and then we need to reach this value, okay? So, and we can't go over this value. So one of our path can be from this to this, then we can go from this to this, then we can go from this to this, then we can go from this to this. So what is the cost going to be in this one? This 1 plus 1 plus 1 plus 1 plus 1. So it's going to be 1 plus 1 plus 1 plus 1 plus 1 plus 1. So it's going to be 5. So I think I wrote 1 extra. Yeah, 3 plus 2, 5. Another path can be via this route, and then we'll go from here to here. And again, the cost is going to be the same in this one. So we need to find the minimum cost that we are going to reach from the value 0 to n-1, m-1 such that we're not going over a value that is -1. So if we see another example, so the answer is 5, which is correct. So if we see another example, that is this. So over here it's majorly same, but we just have one extra restriction that we can't go over this value. So here we need to go from this to this, but we can't go over this and this value. So our path is not going to go over this, it's always going to start via this. So one can be we go from here, then we go to this value, then we go to this value, and then via this we go to this value. So it's going to be 1 plus 1 plus 1, 3 plus 1 plus 1, 5. So the answer is again coming out to be 5. And as we see, it's 5. So we will follow the approach. We can do a DFS traversal on our grid, and if we reach the last value, we'll store the minimum of the global value we have taken, for example mini, and the value that we were calculating side by side to reach that place. And third, we will mark our visited vector side by side. And since, as you saw here, if we go through this path, it's done. We stored one answer, but we also need to check this path, right? So we need to backtrack such that our visited does not become visited for the whole duration. Like if we start checking by this, we want our visited to be back to normal, not and we are able to go through this value. So backtrack after the operation. Okay, so let's see the code for this. So this is our function. First we have added a base condition that if grid 0 0 or grid n-1 and m-1 are -1, then there's no possibility that we are going to reach. So in that case, just return -1. Then we have created a visited vector of bool, and we have added true to this value 0 0. Okay, now we are performing a DFS function. In the DFS function, we are checking the minimum cost. That in here we are checking if we have reached the last value or not. If that is yes, then we are calculating the mini value and we are returning it. Else we are checking the 4 direction, that is up, down, right and left via this, and here are the direction that we have made, and we have given the is valid condition in another function so that it's more compact and easy to understand. And we are checking if it is valid, then we'll add the visited to be true. We are performing DFS, and here we are backtracking it. Okay, so that if we want to do another operation, we just don't get stuck in a visited way. It's back to normal over here. So this is what's happening, and at the end we are getting the answer via this. That's the solution for this question. Thank you. Hello everyone, so today we are going to solve another question on Unstop practice, that is library of forbidden constructs. Now the problem statement is, in the library of forbidden constructs there are n magical scrolls. Some scrolls contain knowledge so dangerous that they can only be read after reading one or more prerequisite scrolls. Each scroll has 0 or more dependencies. A scroll cannot be read unless all its prerequisites have already been read. Your task is to determine whether it is possible to read all scrolls without violating any prerequisite condition or not. If possible, print one valid reading order that satisfies all dependencies. If it is impossible due to cyclic dependencies, print impossible. Among all possible reading order, you must print the lexicographically smallest valid order. This means scrolls with smallest ID should appear before earlier where they are possible. Okay, so let's try to understand this via our question. And our input format is, the first line contains two integers n and m, number of scrolls and the number of dependency rules, and then we have the dependencies. So here we have 4 scrolls and 4 dependencies. Now as we see, it states that two integers a and b, denoting that scroll a must be read before scroll b. That means b is dependent on a. So if we start from here, we have 1 and we see that 2 is dependent on 1, right? Now I need to just, or wait, I'll make this file. We have 4, so I'll just add 4. One and 4. Now as it says, 2 is dependent on 1. So 2 is dependent on 1. 3 is dependent on 2. 3 is dependent on 2. 4 is dependent on 3. 4 is dependent on 3 and 2 is dependent on 4. So if we see, we get a cyclic format, and it clearly said that if we get a cyclic format, then it is impossible to make this one. So the answer here will be impossible, because in order to do this we need this, for this we need this, and for this we need this. So we get stuck in a loop. So it's impossible to do this one. So the answer here is going to be impossible. Now let's try out this example. Here we have 6 scrolls and 6 dependencies. So I'll just make the graph for this. 4, 5, and we have 6. Now 3 is dependent on 1. 3 is dependent on 1. 3 is also dependent on 2. 3 is also dependent on 2. Now we are here. 4 is dependent on 3. 4 is dependent on 3. 5 is dependent on 4. 6 is dependent on 4. And we have 5 dependent on 2 again. So if we see, there is no cycle that is being made. Everyone is connected to a different node and it's open in a way. Like there is no cycle. This representation might be a bit cluttered, but overall there is no cycle that is being formed. So if we try to find the end degree of all these values, then it's going to look something like end degree. We have 1, we have 2, 3, 4, 5, 6. Now let's see the end degree of these values. End degree of 1 is 1. Only one node. Only this node is coming over here. Then end degree of 2 is 2. These two values are coming. Then end degree of 3 is 1. End degree of 4 is again 2. End degree of 5 is again nothing, 0. No node is coming over here. And then end degree of 6 is again 0. So we are going to solve this via pushing it in our queue via a BFS approach. So if we push the values that are 0 in our queue, there is going to be 5 and 6 going in first. Then we are going to check the neighbors of 5 and 6. Who are the neighbors? Who are the values that 5 and 6 is dependent on? 2 and 4, right? So we will consecutively decrement the end degree of 2 and 4. If 2 and 4 become a value that has end degree 0, then we will again push it in our queue. So our approach is going to be make the adjacency list, get neighbors, then make the end degree vector, push values with end degree 0 in queue. Start checking in queue and push in answer vector, then iterate over neighbors of these nodes. So let's just start coding now. First and the foremost thing is going to be a adjacency list. Since it's a 1-based indexing, we'll use n+1 and I'll just make the end degree side by side. Now we want to add in an adjacency list the from values to our to values. So we'll add to dot pushback from. What I mean by this is, when we start checking over here, we want that if we are checking 5, we get the value 2 and 4. But if we start checking over here, it's 5 and 4 and 5. Or it's 2 and 5. So we were pushing the from value to our to value. That's what's happening over here. And in end degree, we're just incrementing the from value. Okay. Now we make the queue. So for equals to 0, just push it. Next is we'll just make our answer vector. This is what's happening over here. Now we'll just sort our answer vector because it always to return the lexicographically sorted value. Now if answer dot size is less than n, cout impossible and return an empty vector, else return answer. Let's try to check this. Yeah, let's submit our code. And it's the correct answer. So this is the solution for this question.
Hello everyone, so today we are going to solve another question on Unstop practice, that is Islander's trade route dilemma. Now the problem statement is you are a trader navigating through an archipelago of N islands connected by M directed sea routes. Each island offers a unique type of good represented by an integer from 1 to N. You begin your journey from island 1 and your goal is to reach island N while connecting at least k distinct types of goods along the way. Traveling from one island to another via sea route consumes time. Once you collect a good from an island, it starts degrading and becomes worthless after X time units. Only the goods that are still fresh when you reach the island N are counted. You must determine the minimum freshness threshold such that there exists a path from island 1 to N, collecting at least k distinct goods and that are still fresh upon the arrival. If no such path exists, print -1. So let's understand this problem by this example. Okay, so in this example, we have 4 islands, we have 4 sea routes, and we have 4 is the minimum number of goods that we reach at the end when we are at the nth island. And these are at the goods at each island. What I mean is at island 1, we have good 1. At island 2, we have good 2. At island 3, we have good 3. At island 4, we have good 4. Okay, so these are the goods at each island, and this is the sea route. For example, from 1 to 2, we'll reach 3. We will reach in 3 time units. From 2 to 3, we'll reach in 2 time units. Okay, so we need 4 goods. So at the end, that means from 0 to n, we need all 4 of them. 1, 2, 3, 4. All 4 of these goods are required. So one of our path can be from 1. We can go till 2. From 2, we can go till 3. From 3, we can go till 4. And at 1, we can collect. At island 1, we can collect good 1. At 2, collect 2. Similarly, we can collect all 4 of them. The time will be, we'll start 1 at 0. Then at 2, it's going to take 3. So it will become 3 over here. Then from 2 to 3, it's going to take 2 time units. So 3 plus 2 is going to be 5. And from 3 to 4, it is going to take 3 time units. So 5 plus 3 is going to become 8. So 8 is the time that we will need to reach from 0th island to nth island, or from first island to the nth island. And since 8 is the time that we need, that means 8 will be the minimum threshold that the question is asking, the minimum freshness threshold required, because that is the time that any good will reach from first island or second or third or fourth, and it will not drop. For example, if we check for good 1, time is 8, right? So we find good 1 at the 0th time. So it is going to be at the end, it's going to be at value 8, which is greater than 0. So it's valid. Then we check for good 2. Now we find good 2 at which point? At 3. So it is going to be 3. Now this is 5, which is also greater than 0. So it's also valid. Now we find good 3 at which position? We find good 3 at position at time 5. So this is going to be 3, which is also greater than 0. So this is also valid. And similarly, good 4 is at 8. So 8 minus 8 is equals to 0, which is also not less than 0. So valid. So that is why 8 is going to be our answer. So as you see, 8 is our answer. So let's also try this example, because this is a very complicated question. So herein we have 5 islands, 6 routes, and 3 is the minimum number of goods that we need. So as we see, the products or goods on each island are on first, second, third, fourth, and fifth. On island number 1, we have good 1. On island number 2, we have good 2. On island number 3, we have good 3. On island number 4, we have good 2 again. And on island number 5, we have good 5. Okay, and it says we need 3. So we can get any 3. 1, 2, 3, or 1, 2, 5, 2, 3, 5, 1, 3, 5. Any order can be followed. So one path can be from 1, we can go till 4, and then we can go till 5. So let's see the time that will be required. So 1 to 4 is going to take 3. So we start from 0, then we'll be at 3, and then from 4 to 5, we are going to need 5. So 5 plus 3 is going to be 8. So at the end, it is going to be 8 time units. And we covered 3 goods in it. That is the minimum required number. So at first we got 1, at fourth we got 2, good 2, and at fifth we got good 5. Now we can try path 2, that can be from 1 to 2, then 2 to 3, and then we can go from 3 to 5. So let's see about that. 1 to 2, then to 3, 5. So this will again start at 0. Now 1 to 2 will take us to 4. Then from 2 to 3, we are going to be at 5. 5 plus 4 is 9. Now 3 to 5 is 6. Now 9 plus 6 is going to be 15. So time is going to be 15 time units in this one. And we are going to cover 4 goods. That is 1, 2, 3, and 5. Which is not needed because we are satisfied with 3, and also the time is also minimum in this. This is a greater time, and it asks us to find minimum time, minimum threshold. So again, the answer here is 8. So the approach we are using in this is graph with a binary search, right? So binary search will be used to find X threshold time. So our low will be 0 and our high is going to be any value, like let's assume 189. Then we'll find the mid value. Now we'll check if this mid value, for example, our function is solve mid, if this mid value follows the condition or not. If yes, then answer is mid, and then we are going to search in a value less than this. Like this is what we do in binary search, right? We reduce the search space. So now our high is going to be mid minus 1. And if not, we're not finding the answer here. So we are just going to increase our search space. Then low is going to be mid plus 1. Okay. But you might be concerned what this solve function is going to need. So this solve function is first going to store everything in a priority queue. Like we're going to follow Dijkstra algorithm to find the path. In the path, we are going to check what was the time that was needed in order to reach the nth node, and how many goods we covered in that. Is it greater than or less than the number of k required goods, and what is the current time. So by that we'll calculate it. So let's see the code for it. So first of all, we made a graph to store these values from our edges. Then we have started our binary search algorithm. Here low is this, high is this, answer is -1. And can we reach with freshness is the function that we are using. If it is true, answer is mid, and then we are reducing our search space over here. Else we are increasing our search space because we could not find the answer in this one. And at the end we're returning the answer. So here, let's check out this function. So in this function, first of all, I made a structure state wherein I'm going to store the node, the time that was required to reach the particular node, and all the goods that have been collected so far. And this is the function that we use in a min heap in order to store the minimum value at top, because by default a priority queue always is a max heap and it's going to store the positive value at top, but we want the smallest value at top because we need the lowest minimum time that we in order to reach the values. So we made a priority queue based on that. The priority queue is going to store the node, the time required to reach the node, and the number of collected goods that we have collected so far. So in the beginning, we just initialized our priority queue with 0, 0 and good 0, whatever we have found so far. And then we started iterating over it. So now we are checking if our node is n minus 1, that is, we have reached the final node. Like if we check from here, our final node is going to be what? 4. If node is equals to n minus 1, that means we have reached the end. So now we'll check for the fresh count. What is fresh count? Fresh count is the number of goods that we have found so far. So we're just going to count it over here using our unordered map, and our unordered map here for storing these collected goods. So we are going to just count it, and if this value is greater than equals to k, then return true because this is a correct valid operation. So this is what will return true. Now after this we are going to check the neighbors. Is there any neighbor of the particular island that we have not checked so far? If yes, then we are going to collect it and push it in our collected goods order. And after that we're going to check all nodes and check over their values 1, 2, 3, 4, and we are iterating it in good keys. What I mean by that is it might be a bit complicated to check these, right? So we have made keys for this and push them in here so that we follow a simple and not complicated form to check this. And if none of these are followed, then we return false at the end. And via this, we can get our answer. Yes, so it's running fine. Let's try to submit this. So 2 test cases are failing, but I think there is an error over here because I tried to submit this code before and at that time it was running fine. So this is the same code, exact same code. So there might be some internal error right now, but this is the right code for this. So thank you for watching.
If you are someone who wants to try out the weekly coding challenge, then quickly go in the link given below and register for it. This week's coding challenge will happen again on Sunday. Till then, stay tuned for many more fun resources coming your way on Unstop Unhinged. Don't forget to like, share, and subscribe.